Our universe has a beginning. It's not eternal. It had a starting point, a moment when everything we know and see today came into existence. It burst into existence an astonishing 13.8 billion years ago, marking the dawn of time and space. This event, the Big Bang, wasn't an explosion in space but rather the expansion of space itself, stretching and growing from a minuscule point. Imagine the entire universe, everything we see today, compressed to an incredibly tiny point, smaller than an atom. This point, hotter and denser than anything we can imagine, represents the very beginning of time and space as we know them. It was a singularity, a point of infinite density and temperature. In that first infinitesimal moment, the universe was a roiling sea of energy, a place where the laws of physics as we understand them break down. It was a chaotic, turbulent state. From this chaotic beginning, the universe began to expand and cool, gradually transitioning from a hot, dense state to a cooler, more stable one. As it did, energy began to transform into matter, following Einstein's famous equation E equals mc squared. This transformation was crucial for the formation of the universe as we know it. This marked the birth of the first fundamental particles, the building blocks of everything we see around us. These particles would eventually come together to form atoms, stars, galaxies, and all the structures in the universe. In the earliest moments of the universe, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single superforce. However, as the universe expanded and cooled, this unity began to break down. Like a cooling metal that solidifies into different shapes, the forces began to separate. First came gravity, the weakest but most far-reaching force, responsible for the large-scale structure of the universe. Then, the strong nuclear force, responsible for binding quarks together to form protons and neutrons, became distinct. This epochal separation of forces set the stage for the emergence of quantum electrodynamics, or QED. Quantum electrodynamics, or QED, is the theory that describes how light and matter interact. It is a cornerstone of modern physics, providing a comprehensive framework for understanding the fundamental forces at play in the universe. It's one of the most successful theories in all of physics, renowned for its astonishing accuracy in predicting experimental results. The precision of QED has been tested and confirmed through countless experiments, making it a vital tool for physicists. QED governs the behavior of electrically charged particles, such as electrons and positrons, and their interactions with photons, the particles that make up light. These interactions are not just theoretical, they have practical implications in technology and everyday life. These interactions are responsible for a wide range of phenomena we observe in the universe, from the behavior of atoms to the light emitted by stars. The principles of QED help us understand the very fabric of reality, from the smallest particles to the vastness of space. At the heart of QED lies the concept of the quantum field. This field is a fundamental entity that exists throughout the universe, influencing everything within it. These fields permeate all of space and time, and particles are simply excitations or vibrations within these fields. This perspective revolutionizes our understanding of what particles are and how they behave. When particles interact, they do so by exchanging photons, the carriers of the electromagnetic force. This exchange is the fundamental process that underlies all electromagnetic interactions, from the simplest to the most complex. To understand the complex interactions of particles in QED, physicists use a powerful tool called Feynman diagrams. These diagrams, named after physicist Richard Feynman, provide a visual representation of particle interactions. Imagine these diagrams as little space-time stories. Lines represent particles traveling through time and space, while vertices, or points where lines meet, represent interactions. By following the lines and vertices, we can track the movement of particles and the exchange of photons during an interaction. Feynman diagrams allow physicists to calculate the probability of different outcomes for a given interaction. The elegance and simplicity of these diagrams have made them an indispensable tool for understanding the quantum world. Section 5. Creation and Annihilation, the Cosmic Ballet. In the hot, dense environment of the early universe, QED was in full swing. One of the most remarkable phenomena governed by QED is pair production. where energy can be converted into matter and antimatter particles. Imagine two high-energy photons colliding. In this collision, the energy of the photons can be transformed into an electron and its antiparticle, the positron. This process, a direct consequence of Einstein's E equals mc squared, demonstrates the intimate relationship between energy and matter. Just as energy can create matter, matter and antimatter can annihilate each other, releasing energy in the form of photons. This dance of creation and annihilation played a crucial role in shaping the early universe. Section 6. Echoes of the Big Bang, the Cosmic Microwave Background. As the universe continued to expand and cool, a pivotal moment occurred around 380,000 years after the Big Bang. Before this time, the universe was a hot, opaque plasma, where photons were constantly scattered by free electrons. However, as the temperature dropped below a critical threshold, electrons combined with protons to form neutral hydrogen atoms. This event, known as recombination, allowed photons to finally travel freely through space. These ancient photons, stretched to microwave wavelengths by the expansion of the universe, form the cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang provides us with a snapshot of the universe as it was just 380,000 years old. Section 7. QED's Legacy, a Triumph of Modern Physics. Quantum electrodynamics stands as one of the most successful theories in the history of physics. Its predictions have been experimentally verified to astonishing precision, making it a cornerstone of our understanding of the universe. QED has not only deepened our knowledge of light and matter, but has also paved the way for technological advancements such as lasers, transistors, and modern electronics. Its influence extends far beyond the realm of theoretical physics, shaping our everyday lives. The development of QED represents a triumph of human ingenuity and our ongoing quest to unravel the mysteries of the cosmos. It serves as a testament to the power of theoretical physics to illuminate the workings of the universe at its most fundamental level. Section 8. Unification, the quest for a theory of everything. While QED, or quantum electrodynamics, has been incredibly successful in describing the electromagnetic force in great detail, the quest to unify it with the other fundamental forces, including gravity, continues to be one of the most profound challenges in physics. This search for a theory of everything drives much of modern theoretical physics, inspiring countless hours of research and debate. Physicists believe that at extremely high energies, such as those present in the very early universe just moments after the Big Bang, all four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single superforce. Finding a theory that can describe this unification is one of the greatest challenges in modern science, requiring new ideas and innovative approaches. The quest for a unified theory is a journey into the unknown, a voyage that pushes the boundaries of our understanding of the universe and its fundamental laws. This journey is not just about solving equations, it's about pushing the boundaries of our understanding of the universe, exploring new realms of possibility. It's a journey driven by curiosity, imagination, and the unyielding human desire to comprehend the cosmos and our place within it. The quest for knowledge is endless. Don't forget to subscribe to the channel for more content on cosmology and fundamental physics. Stay curious and keep exploring the mysteries of the universe.